In this video, we'll talk about problem number 6 from the 2003 AP Calc AB free response set. This is a non-calculator question, and in this video we'll take a look at parts A and C having to do with continuity and differentiability. So in the problem, they define a piecewise function for us. It's defined as the root function at 0, at 3, and at all values in between those. And then from 3 up to 5, including 5, it's defined as this line, 5 minus x. In part A, we're asked to figure out if the function is continuous at 3, and if it's not, we want to say why. So what I'm going to do is I'm going to start with the definition of continuity, and that's a three-part definition. I'm going to kind of ask this in question form. First thing that has to happen at a point in order for us to be continuous there is the function value has to exist at the x value we're considering. So does f of 3 exist, or is f of 3 defined? So if we're trying to find f of 3, look at these intervals. The value of 3 is included on this interval. So if I'm trying to find f of 3, that's just going to amount to me taking the root function, since that's the definition of this function that includes that x value, and evaluate, and what I end up with is square root of 4, which is 2. So does f of 3 exist? Yeah, of course it's 2. So yes, we are good to go there, and now we're on to the second piece of the definition of continuity. The second thing that has to happen at a point in order for you to be continuous there is the limit as you approach that point has to exist. So does the limit as x approaches 3 on this function exist? And if we look at the way the function is defined once more, we have to worry about this limit not existing, because on the smaller side of 3, our x values are going to be here, and we're going to be using this definition of the function. And on the bigger side of 3, our x values are going to be found here, and we're going to be using the linear definition for the function. So since this is a piecewise function, we're going to have to definitely break this up into one-sided limits. We're going to have to consider approaching 3 from the smaller side on f of x, and also approaching 3 from the bigger side on f of x. So if we consider these one-sided limits, on the smaller side of 3, x values beneath 3 are here, so we're going to use the top definition of the function, and if I can get away with it, I want to put the x value I'm approaching in place of that x and see if I get an answer. And we actually already did this. We evaluated the top definition of the function at 3 when we were considering whether or not the function value existed there. So the limit as we approach 3 from the smaller side using the top definition of the function is going to be 2. Now, approaching 3 from the bigger side, well, values bigger than 3 would be on this interval, so we'd be using this definition of the function, and if we take that definition of the function and put the x value that we're approaching in place of the x, we get 2 there. Since these one-sided limits are equal to each other, they're both equal to 2, does the limit exist? Yes. So we're on to the third part of the definition of continuity, and the third part is whether or not the function value, which would be f of 3, does that equal the limit as x approaches 3 on the function? Do those things equal each other? And of course, we found the function value in the first question here. We got 2 for that. The limit is equal to 2 since the one-sided limit's both equal to 2. So does the function value equal the limit? Yes. And because each of these 3 conditions are satisfied, we know that our function is continuous at x equals 3. So we're going to skip ahead to part C of this, which has to do with differentiability. And they give us this new function g of x. And this function g of x has these unknown constants in it, k and m. And it's a very similar definition to the definition for f of x, but it is slightly different. We still have a root function for the interval 0 to 3, including 3, and then we have a linear function from 3 to 5. We want to figure out what the values of k and m are, these constant values, in order to make the function differentiable at 3. Now, this is kind of a two-step process. If we have a piecewise function where we have at the x value of 3, or we have a root function that takes us to a certain point and we leave off at the x value of 3 with a closed circle, if the linear function picks up above the root function or below the root function, we're definitely not going to be differentiable because we're not continuous there. So one of the conditions for being differentiable at a point is that you're continuous at that point. you can't have your derivative exist at a given location unless you are continuous there. So we're going to have to make sure we're continuous, meaning that at 3, this expression is going to have to equal this expression, which basically forces the closed circle where the first piece of the function leaves off to be in the exact same location in the coordinate plane where the open circle where the second piece of the function picks up at is. Now the second piece to this process, and that was a pretty bad y-axis, but we'll try to make do with it. The second piece of this is going to be if you have the root function leave off and the linear function pick up in the exact same location, so I'm just kind of putting my open circle around the closed circle, we're continuous here. If the slope of my tangent line on the root function at 3 where I leave off is something like positive 1/2, and then the slope of the tangent line on my linear function ends up being something like positive 2, I have this cusp at 3. I don't gradually cross all slopes between 1/2 before I get to 2. I jump straight from a slope of 1/2 to 2, and I have a cusp there making me not differentiable. So not only will the function values have to equal each other to ensure that we're continuous, but the slopes are going to have to equal each other. Now to ensure the function values equal each other at 3, all we're going to have to do is equate the top definition of the function with the bottom definition of the function when x is 3. And if we simplify this a little bit, that's a 4, and the square root of 4 would be a 2. So we get 2k equals, over here we'd get a 3m plus 2. Now the reason why this alone doesn't let us figure out what the value of the constants would need to be is because we have 2 variables or 2 unknown constants in this equation and only one equation to use. So what we also need to do is we're going to need to take the derivative of g and make sure the slopes of the tangent line equal each other at the transition value of 3. So I'm going to take the derivative of g in a piecewise form here. G prime of x is going to be equal to one thing in between, and that was a bad curly bracket, but I was trying to draw one of these there. We're going to try to take the derivative of this. So if I change the root to a quantity to the 1/2 power, I'm going to multiply the k by 1/2. So I'm going to have 1/2 k, and then I'm going to have the exponent decrease by 1. So it's going to go down to negative 1/2. I'm going to have the inner function here still, and then I'm going to finish the chain rule, multiply by the derivative of x plus 1, and I get 1. M is a constant, so when I take the derivative of the second piece of the function, I'm going to take the exponent on my x, which is a 1. I'm going to multiply the m by it, and that's going to give me m x to the 0, which is just m, and then the derivative of 2 is 0. So here is our derivative. We need the derivative to be equal to each other at the transition value, the derivatives to be equal to each other at the transition value of 3 as well. So what I'm going to do is I'm going to simplify the top derivative. So I'm going to have a k in my numerator with the 1. I don't really need the 1, but I have it there already. I'm going to have this go back across the fraction bar into the denominator since it has a negative exponent on it, and I'm also going to change it back to a root. So this is a little bit simpler to deal with, and that's a sloppy k there, but it is a k. And what I want to do is I want to equate the derivative, m, with this derivative when x is equal to 3. This derivative is always m, but at 3 the value of this derivative is going to be k over 2 times the square root of 3 plus 1. And I want to equate my derivatives. This simplifies quite a bit. I can go ahead and add those together, get a 4. Square root of 4 is 2. 2 times 2 in that denominator gives me 4. So I have k over 4 equals m. Now I have this equation that has an m and a k, this equation that has an m and a k. If I treat this like a system and use substitution to solve, I'm going to have my answer for k and my answer for m. So I'm going to substitute this expression, k over 4, in place of the m over here. And if I do that, I'm looking at 3 times k over 4 plus 2 equals 2k. This is 3/4 k. If I subtract 3/4 k from 2k, what I end up with is I end up with 5/4 k, and that's going to equal 2. So I'm solving this for k. If I multiply by 4/5, what I end up with is k is going to have to equal 2, 8 over 5, and I can substitute 8 over 5 in place of this k. to solve and get my answer for m.